Hello, good evening, class. In today's class, I'll be solving the assignment of the previous year. That's what I'm supposed to be. And so I'll start with the first question, that if the Fermi energy of a silver is so I'll start with the first question, that if the Fermi energy of a silver is EF is given, that is 5.52 eV electron volts, and its resistivity at room temperature, so rho at 300 Kelvin, is given as 1.62 into 10 power minus 8 ohm meter. And the question asks the corresponding velocity of the conduction electron and the average time between collisions. So this is asking, hello, yeah, Hemant, tell me. Yeah, so the question is asking the corresponding velocity of the conduction electron. So we know that the corresponding velocity of the conduction electron will be nothing but it's a free particle. That's what we assume because no potential is given, and EF is half mv square. So this implies the V is 2 m under root 2 e by m. Since no effective mass is given, so I will take me as the mass of the electron, that is 9.110 power minus 31 kg. EF is already given 5.52 eV. I will convert into joule. So to convert into joule, I'll have to multiply it by charge, electronic charge, that's 1.610 power minus 19, that will be joule. And if I compute it under root 2 times 5.52 times 1.6 times 10 power minus 19 by divided by mass of electron, this gives me the value of, so this I have already calculated, so I know this value. You can do this just in simple mathematics, you can do it, and this will turn out to be 1.39 into 10 power 6 meter per second. So this is the velocity of the conduction electron, which are very close to the Fermi level. So they are the conduction electron. Now the second question is the second part of the question is what the average time between collisions. So this is the relaxation time tau. So second question is average time between the collisions. We know that sigma is ne square tau by m, and this, and I can write it as 1 by rho, that is the resistivity, ne square tau by m, and what I have to compute is tau, so that will be m by rho ne square. So rho has already been given, that is 1.62 in 10 power minus 8 ohm meter. Rho I know, effective mass I will treat as to be the free electron carrier mass, and electronic charge I know. All I'll have to know is n, what is the carrier density. So the Fermi energy is given, so I can compute the n. So we know that Fermi energy is given as h bar square. This is from the class notes, you can refer. 3 pi square n to the power 2 by 3. And if you do the reverse of it, like if you write it in the form of n, then you can write it as 1 by 3 pi square and 2 me by h bar square to the power 3 by 2. You can feed in the value of the E, M you already know, electronic, the effect 9.1 10 power minus 31 kg mass of electron. H bar square, so H bar is 1.05 10 power minus 34 joule per second, and this pi you already know, 3.14 22 by 7. If you feed this information, your n carrier density, I'm writing it, you can work it out, it's easy, and the n will turn out to be some 5.88 into 10 power 28 electrons per meter cube. So this is roughly the carrier density of the charge carriers in silver. So this is the number which has been computed using the given Fermi energy. Now I'll feed this in this equation number 1. So if I feed it in the equation number 1, so my tau will be given as m by rho n e square. M is 9.1 into 10 power minus 31 kg. Rho, the question tells me that it's 1.62 into 10 power minus 8. Dimensions are ohm meter, so I don't have to worry about the dimension, because everything I'm dimension. Whenever you solve such questions, make sure that the dimensions are right. They can give you the factor, the powers, and then e square is 1.6 into 10 power minus 19 to the square. So you can just work it out. 9.1 10 power minus 31. It's 1.62 into 5.88 into 1.6 square, and the power, if I solve, 19 38 plus 28 minus 8. So this will be some 9.1 into 10 power minus 31. 28 is minus 18. That goes above and makes plus 18. 1.62 into 5.88. 1.6 square. And if you solve it down, it will roughly turn out to be, so yeah, it will turn out to be 3.7 to 10 power minus 14. This will be, since this is relaxation time, so this will be in seconds. Yeah. So this you can work it out. So the relaxation time which we have computed is 3.7 into 10 power minus 14, and the VF is 1.39 into 10 power 6. This gives me the correct answer to be C, where the VF is given as 1.39 10 power 6 meter per second, and the average time between the collision, that is the relaxation time, is 3.7 to 10 power minus 14 seconds. If you have any questions, you can ask me. So I will be solving the similar problems which are there in your assignment, not the exact one. One or two may be the similar, because these are the previous year problems, not the current year. And this is what I have been instructed from the NPTEL team to solve the previous year problems. Any question? Okay, so some question is there. Just put the chat. Yeah. Just wonder whether the Fermi energy changes with applying bias or incidence of a particular wavelength light. See, so when you apply a bias, so it's a very good question. So when you apply a bias, so what happens? The band bends. So on, for example, what this means is like, this is a very naive picture. Actually, the picture which we are solving has many drawbacks, and this is not the right picture. The right picture, how the electron moves. So you have your metal, for example, that's a silver it is, and you apply a positive voltage here, V, and you ground it. So what happens? According to Drew, the electrons will go collide with each other like this, and they will move with a drift velocity Vd. This tells me that all the electrons in the band starts moving. But I know that's not the case. The contribution only comes from the electrons which are near the Fermi energy. So if my band is still filled till this point, the contribution only comes from these electrons, not the very, not the below the filled electrons. The contribution comes only near to the Fermi energy. So the Drude picture is not very right, but like addressing your question, like if you apply a bias, right, in this picture, what will happen? Your band, which was like initially, now you this is bias 0 is equals to 0. When you apply a bias, so your band will be somewhere like this. So initially the states will feel like till this point. Now it will be tilted, and this picture tells that okay, this is how the electron flows. But this picture, this is from the Drude kind of the thing, finite bias, band bending. We call it the band bending. But this picture is not very right. If you see it, how the electrons flow actually is governed by this simple phenomenon. For example, you have your this point, right? Contact. This is you call a contact one, contact two. This contact you apply a large bias V, and the contact B you ground. So you set it to 0. So if I draw the potentials at these points, these are my A and B. So the levels are filled till this point. This is my, and this is my 0. This is V is equals to 0. And this difference between these levels, let me just draw it like this. This difference is V. That is the bias which you apply. And now your band is somewhere like this. So what will happen? The electrons which are here, till in this region, they want to go and want to go to this contact. They want to fill this band and want to go to the B contact. So this range of your near the Fermi energy, where your Fermi energy lies, they contribute. But if you come down in the system, like for example here, this wants to fill it up, this also wants to fill it up. So there is no conduction from the electrons, which are, this is EF, my Fermi energy. So there is no conductions of the electrons, which are well below the Fermi energy, because both the contacts want to fill it up. Similarly, on the top here, both the contacts wants to get emptied. So there is no net current. That's why there is no net potential difference which can make the electrons flow. So the only contribution comes this V. Whatever bias you apply, those many EV. So the energy range will be given as EV. So the carriers which are below and above the EV range, they will only contribute. Other electrons will not contribute in the conduction. And that's how the Fermi energy gets changed in the at interface of two unequal Fermi levels of functional materials. They say as bias on the band, Fermi level will be lifted. Is it really so? See, what do you, then again comes the point, what do you call a Fermi level? Fermi level. So Fermi level we generally define, right? In the case of the metals, again I'm saying in case of the metals, in semiconductors, it gets slightly modified. So if you see the Fermi level, how you define your band is there, and it is the level EF at temperature T is equals to 0, which separates the filled band and the unfilled bands. This is the EF. When you apply, it is not like the real picture. If you go quantum mechanically and see the single edge states, the real picture is not like that. The band gets banded. If it's a single channel, the band will not like band. It is like a ballistic transport, and all the states which are there will contribute. But if it is a diffusive transport, which is there in the metals, then how the potential will look like is, and then in that pictures for the diffusive regimes, like the metals generally, because electron collides with respect to each other, there the band bending theorem works finally. The reason being the potential will follow this trend. the potential will fall like this. This is my potential line, this is my x-axis, this is my v, this is v0, this is v0. So if you see it, it has a slope. So you can think it like the band has got bended, and that is allowing the electrons to flow. So in the metal, in the diffusive regime, band bending pictures work fine. So works fine. But as you go to single channel seats, like ballistic transport, in the ballistic transport, the profile of the potential will be somewhat different. Is equals to 0. This is my V. So it's E mu. Mu is EV. This is V. This is 0. Your chemical potential is EV. You lifted it by EV. And in this case, the potential profile will be like this. And then suddenly it will go to 0 near this contact. Similarly, there will be a line which will be coming from this end. You suddenly go to 0 at the contact. So the potential lose is not throughout in the bulk, it is only happening for the edge states. This is for the edge states. Single channel, ballistic channel. There is no collision between the electrons, nothing. There is a single channel which goes like a bullet. That's why it is called ballistic transport. And here, the resistance comes only from contacts. Here, only contacts. And that resistance is also quantified. If there is a single channel, then resistance will be single ballistic channel. That's the so that's the standard resistance. This is 25 kilo ohm. This you will come to know whenever the faculty starts, the professor start teaching the quantum hole mechanics, quantum hole physics, because those things cannot be explained by the Drude model. Drude is all about the bulk, not about the edge transport and all those things. The bending picture works for metal. Yeah, in the ballistic transport, Fermi level does not change. The potential profile is like this. One of the edges will for your Fermi level will remain same, and it will go like a bullet. See, Fermi level you define again. Fermi level you define for bulk. Define for bulk. Whenever you talk about the edge transport, you don't define the Fermi level exactly, because now the conduction happens at the edge of the sample. Not the bulk is insulating. Your bulk is insulating, and conduction happens only through edges. Like this edge will take the current like this, and there will be another line which will be empty. So this is for edge states. So whatever the Fermi level concept you define all those things, this is for the bulk transport, and they will talk about the system which is infinitely large, so they don't care about the edge states. But in real systems are finite, they have their edge, and if the bulk is insulating and the conduction happens only through edges, then yeah, these things holds. Okay, now if this is clear, so I will move to the next question. And the question is, if the average time between collision in copper is tau is given, that is 2.3 into 10 power minus 14 seconds. Its thermal conductivity is also given, kappa, that is okay, kappa they are asking in the question. And the Weidmann-Franz constant, CWF is given 2.31 into 10 power minus 8. Weber ohm K minus Kelvin minus 2. So from the Weidmann-Franz law, we know that K by sigma T is a constant, and that constant is CWF, basically Weidmann-Franz law constant. So the question has given us the average collision time. So we know that sigma is n e squared tau by m. Right? Sigma is n e squared tau by m, and temperature also is given. Kappa we have to extract. Okay, so let me just feed in the information. Kappa is equals to CWF times sigma times T times sigma is n e square tau by m. So here I will just take the values of the, since the n is not given, right? N is not given for the copper, but I can take it from the Google. This should have been given. So n for the copper, n for copper. The roughly number density we know in the metal is 10 power 28 per meter cube. So every single question you can solve it with this type of carrier density. But I will take the value of the copper. N for copper is 8.5 10 power 8, 28. E, I know that 1.6 into 10 power minus 19. Tau is given 1 into 10 power minus 31 kg. This gives the kappa to be 2.31 into 10 power minus 8 times n is 8.5 into 10 power 28, and E is 1.6 into 10 power minus 19 square. Tau is 2.3 into 10 power minus 14 divided by 9.1 into 10 power minus 31. If you solve all these equations, so the answer will come out to be roughly around 380 into 10 power 0, 380 basically per meter inverse Kelvin minus 2. So this is what it will be, and that gives me the correct answer to be 376, which is the closest one. I should multiply it with temperature also 300 Kelvin. Yeah. If any question you can ask. So there are limits also in this the Weidmann-Franz law, but in the basically these are the drawbacks of the two-day theory, that it explains it in a temperature range, the far below and far above, but in intermediate range where it increases linearly, and the coefficient, all those things, there the two-day model fails. Okay. If no more question, then I'll start with the question number 3. The density of state function of electron in a metal is given by, so density of state is given. The GE is the density of state, 13.6 into 10 power 27 under root E dE. The Fermi level at a temperature few degrees above absolute zero for copper, which has, okay, carrier density is given 8.5 into 10 power 28 electrons per meter cube, and they are asking for EF. What is the EF? The Fermi level at a temperature few degrees above absolute zero. So they are asking EF. What is the EF? Which is few degrees above the absolute zero. So absolute zero is the temperature at which we define the Fermi level, right? And they are saying that it's few degrees just above the
Fermi level. So if I solve it, then it goes like, we know that the carrier density, the GE, we know GE is nothing but del N by del E, the number of states per unit energy. That's the density of state. So I can integrate it. So my N will be GE DE. So let me just integrate it. That will give me N 0 to EF and 13.6, because I'll have to take the levels which is very like the ground state level, which is 0, the bottommost level, and I have to fill it till the Fermi energy. So that's why I integrate till the EF, and 13.6 into 10 power 27 e to the power half dE. N is 13.6 into 10 power 27. I can take it out, and e to the power 3 by 2 by 3 by 2, and I put it the marker 0 and EF, and gives turns out to be 13.6 into 10 power 27 times 2 by 3 times EF to the power 3 by 2. So EF will be nothing but 3 times N is already given in the question, 28 divided by 2 divided by 13.6 into 10 power 27 to the power 2 by 3, and yeah, and if I solve it, this will be 3 into 8.5, so 10 power 28. Right, yeah, so it can be, let me solve it. Though I have already solved it, but I can just solve it for you. I'll use the calculator. So 3 into 8.5 is 25.5, divide by 2, divide by 13.6. So this will be 0.93 into 10 to the power 2 by 3. That's something that, make sure that, so it will be 9.3 to the power 9.3 to the power 2 by 3. That gives me 4.42. EF to be 4.42. Yeah, so that's the answer for it. EF is 4.42. Yep. Now, so this is 4.42. Now moving to the next. Any questions? This is simple density of state. You have density of state. You integrate it with respect to energy. You get the number density. Number density you are already given 8.5 to 10 power 28, and then you integrate it with the 0 to EF, and then you extract the EF out of it, just in mathematics, and the EF extracted is 4.42. The dimension you can do, like, since the dimension of energy is not given here, if it would have been given, the same dimension would have been there. So I think that looking for the metals, it always remains in EV, so this will be EV from both. Any question? Okay, if no more question, then I'll move on to the next question. which is considered a free electron gas in a 2D. The relation between the electron density n and the Fermi vector kf, I say. Okay. So this is asking that you have a free electron gas in a 2 dimension, not in a 3 dimension. So, for example, these are the 2 dimensions which you have, and this is your Ly, this is your Lx, and in which your 2D electron gas is confined. It cannot move in the z direction, that is restricted. So the electron can move in n in 2 dimension only, Lx in x and y. So it's a 2 dimension gas, electron gas. Question says that what is the relation between electron density and electron density n and Fermi vector kf. So we all know that the total number of states n will be given as integral of 0 to kf course, dk, and each k state d2k, it's a 2 dimensional, so d2k, and each state we know carries space of 2 pi by L, 2 pi by whatever the area of the system is. So here in this case, so it will be 2 pi by Lx, so that the states which will carry the momentum in the x direction, and the 2 pi by Ly for the y1, because for each state, this much is region which you require, 2 pi by Lx and 2 pi by Ly. This much region you require for each state, each single state. So if I draw it like this, these are the available states. So to put one state, you require 2 pi by Lx, 2 pi square by area. Area which there is Lx times Ly. That is the area of this rectangle box. So if I do it, I know that d2k I can write it is like in circle. This is that the area is 2 pi k dk. So 2 pi k dk by, I can take these ones out. So Lx times Ly by 2 pi square 0 to kf. I integrate it. So Lx times Ly is nothing but area. So n by a is 1 by 2 pi square, and 2 pi gets cancelled out. So it's k dk. K dk, I do the integral, it's k square by 2, 0 to kf, and n by a is nothing but carrier density. This is 1 by 4 pi times k square, and then this gives me k square is equals to 4 and 5. Okay, let me look. Okay, it is in terms of n only. Okay, so if you write for n, this is k square by 4 pi, right? But there is a catch here. I did not account for degeneracy. Account. That's why this is for non-degenerate system. Now for degenerate system, in the same space of 2 pi by Lx times 2 pi by Ly, I can have two states, two different states. I cannot have, the Pauli exclusion principle tells me that I cannot have the two states in the same one, two electrons in the same state, right? So, but if the electrons have spin up and spin down, then these are the two different state configurations. So that will give me the degeneracy of 2. So if I account that thing, so then my n will be, n generally we write as g, that is the degeneracy, times that d2k by 2 pi by Lx Ly square. I should have write it like this, 2 pi by square by T to K by 2 pi by Lx times 2 pi by L by. And G is the degeneracy. So in this case, G is 2. That will give me N is equals to K square by 2 pi. But for graphene, like I'm just extending it the problem to the current research is going on. But for graphene, what you have is like along with spin degeneracy, there are valley degeneracy also. So two valley and two spin. So two spin and spin degeneracy is 2. The total is 4, and that total G is equals to 4. That gives me N is equals to K square by pi. So general for 2D, N is equals to G times K square by 4 pi. That's the general derivation if I do. And in the question asked, they say that it's a free electron gas in a two dimension. So no value they have discussed. It's a free electron gas is there. So electrons have both up and down spin. So the G will be 2, and for G is equals to 2, the answer will be N is equals to K square by 2 pi. So the correct answer will be K square by 2 pi. Generally we write it as K is equals to under root n pi. If you look at these two, they are dimensionally incorrect itself. For example, this one and this one, because K has dimension of meter inverse and N has dimension of meter minus 2. So the dimensionally only these two are correct. This is for G is equals to 2, the other one is G is equals to 1. Yeah. Any question you can ask? Okay. If no more question, then I'll move on to the next question, which is that for a free electron gas in a two dimension, the density of state is given by. I see. See, we have already derived the N versus K relation. K we have already derived. That is, N is equals to G times K square by 4 pi. Now I know that for free electron gas, potential is 0, so total energy will be kinetic energy, and I can write it at h bar square K square by 2m. M is the mass of the electron, and then if I substitute it, so N will be G times, and K square I write as E times 2m by h bar square, right? So, and density of states is GE is defined as nothing but dN by dE. So this is question 1. This is 2. Substituting 1 in 2, that gives me GE as G times 2m by h bar square. Or did I do something wrong? G times k square by 4 pi, and then k square by 2 pi. This is, and is G times k square is nothing but k square by 2me by h bar square. This is right. And this is 2me by h bar square. Okay. This 4 pi I forgot to put, and this 4 pi will also come. So this will make it g times m by h bar square pi. Now for non-degenerate system where g is equals to 1, this will be ge will be m by pi h bar 2 h bar square. And for spin degenerate system, so g is equals to 2, which is obviously the case. And your ge, that is the density of state, will be m by pi h bar square. So this is for non-degenerate, this is for degenerate. Since there is nothing in the question, it has not been given that the spin degeneracy is lifted, so I'll go with this one. And anyway, the answer m by pi h bar square is there. The m by 2 pi h bar square answer is not there in the option also. That tells me that the spin degeneracy is not lifted. The system is still degenerate. That m by pi h bar square. Any question? If any question is there, you can ask me. If no more question, then I will go ahead with the next question, which is that for a free electron gas in one dimension, the density of state is given by R. It's an easy one. You don't have to do anything. Just first you have to count the total number of state. That system is 1D. So now it's up to me which dimension I choose. I will choose my preferred to be Lx. You can choose your own Ly, Lz. Results won't change. So my electron can move only in this path. That's the only allowed path I have. Then the number of states will be also in the right the same one. So they will be separated by the distance 2 pi by Lx each state. So to cover a single state, like to cover a single state, I will have to have a region of 2 pi by Lx. In that range only, I can fit an electron, a allowed state where electron can sit or can stay in that region. So the number of state will be, that is n. N will be nothing but dk, that in the k space the allowed region, right? And 2 pi by Lx. So the density of state. So if I take it to the up, so the n by Lx, it will be nothing but the carrier density n in one dimension, and dk in one dimension is nothing but kx, right? If I integrate 0 to kf, so it will be kf. And I know that each h bar square k square by 2m ef. So kf by 2 pi. And I know that this is equation 1, this is my equation 2. I can substitute equation 2 in 1, and that will give me n will be 2m e by under root 2 m e by 2 pi h bar. Though I can also consider the spin degeneracy of 2. So this is degeneracy 2. So this will give me 2. So this 2 will go away. So the n will be under root 2m by pi h bar times e to the power half. Now the question asks me, what is the density of state? So density of state is nothing but number of states per unit energy. That is dn by de. So let's do the math. Then dn by de will be nothing but under root 2m by pi h bar times half times e to the power minus half. So this is dn by de will be under root m by pi h bar and then root 2 times e to the power minus half. That's the density of state. So if you look at in the options, then okay, so this is e to the power minus half. The two options are there on this where e to the power minus half is there. Okay, so let me write in the form they have. So they write m and e inside. So del n by del e will be 1 by pi h bar to 2 times the root m by e. So if you see, this is exactly the d. So d, I can write this as like 1 by pi h bar under root m by 2e, right? This is my GE, tensor state, pi h 1 by pi h bar under root m by 2e. So that's the correct answer. Any question or doubt? If no question, then I will move on. So the next question is the conduction electron density in a copper wire 1 kilometer long is. Yeah, this is an interesting question. This will give you an idea like how the electron moves in a system. This is something good. Okay, so the conduction electron density in a copper wire 1 kilometer long. So a wire is there. The problem says that the wire is there of copper. Since it's a copper, so you can treat it like a free electron gas. A large number free electron carrier density is there, 10 power 28, and the length is 1 kilometer. You can think it like a cable coming from a powerhouse or nearest power station to your home, which is maybe 1 kilometer or 2-3 kilometers far away from you. In this case, it's 1 kilometer. And the carrier density of electron is given 8 into 10 power 22 per centimeter cube. The resistivity of copper at room temperature is also given 2 into 10 power minus 6 ohm centimeter. So this question, I think, and contact terminal. So what they are doing is instead of sending you 240 volt, maybe they don't have the supply, they are sending you only 6 volt. 6 volt battery they have attached. This point is your ground. The time it takes the charge, now they are asking how much time this electron will take to move from this end to the other end, to end A to end B. That's the question. That's what the question is asking, right? So if you see, whenever you turn on the light, what you find is that the bulb lights up instantaneously, right? So the intuitive guess will be like something like 3 into 10 power minus 6, because whenever we turn on the button, the fan starts moving immediately, the light turns off immediately. There is a lag, which is a circuit lag, but that's what the intuition says, that the signal is traveling at a speed which is very fast. And out of the given option, 2 minutes, 16 hours, 503 days, it looks like the A is the answer. But let's work it out and see what is the answer, what is the correct answer. So what it is asking is the time it takes the charge to move from one end to other end. So length you already have 1 kilometer. To take out the time, I know that speed is nothing but distance upon time. So Vd will be d by t. All I have to extract the drift velocity. If I know the VD, I know the D, I can extract the time it will take to move from A to B end. So V, we all know, is nothing but NE is okay. VD is E tau by M, right? And this is the VD, and sigma also I know that NE squared tau by M. So rho I can write M by NE squared tau. So let me take the ratio of it because I have been given this quantity. So E tau by M multiplies by NE square tau by, I should multiply them, not divide them. So VD times rho will be E tau by M times M by NE square tau. So VD times rho will be M cancels out, tau cancels out. So E also cancels out, tau cancels out, M cancels out, E by NE. So my VD will be nothing but E by NE rho. And let's just calculate. Potential is given 1 volt. So electric field will be nothing but voltage by per unit length, V by L. So 6 volt, 6 divided by, it's 1 kilometer, so 1000 meter. That will give me 6 into 10 power minus 3 volt per meter. VD will be 6 into 10 power minus 3 divided by the carrier density, which is 8 into 10 power 22. So 8 into 10 power 28 in meter cube. I have to see the dimensions also. And then the resistivity is 2 into 10 power minus 6 ohm centimeter. So I'll have to convert it into meter. So minus 8. And the electronic charge 1.6 into 10 power minus 19 meter per second. Let's do this calculation. This VD will turn out to be, if you solve it, I have already done it. So, but you can see this 19 and 8 will add up 6 into 10 power. Okay, let me do it. Solar into 8 into 2 into 1.6. It's 25.6. 10 power 1. So this will be 6 divided by 25.6 into 10 power minus 4. So VD will be 6 divided by 25.6. That will be 2.34 into 10 power minus 5 meter per second. So this is your speed. Now the time the signal will take, reach from one end to another, one end to another, that is from A to B, will be, time will be D by VD. D is 1 kilometer, 1000 meter. VD is 2.34 into 10 power minus 5. So 1000 divided by 2.34 will be 427.35 into 10 power 2 into 100 divided by 60 divided by 60. So 4.27 into 10 power 5, right? This will be 10 power 5. And if I do it, divided by time, it will be 494 days. So the electron will take 494 days to go from the powerhouse to your home. If this is your home, this is your powerhouse, and the line is 1 kilometer, then electron will take 494 days. That is roughly 503 days. If I do some calculation, take the exact values, it will be 503 days. So that's the closest one. Then can any one of you answer me that why it is like this? The electron is taking 500 days to go from point A to point B, but the light which I turn on lights up instantaneously. It's not like powerhouse turns on your light and it comes after. This is like 2 year, right? 365, 1.5 year roughly. So, but as soon as the powerhouse turns on the light, your home gets lighted up, right? So, is there anyone who can like tell me what's going on here? So, where are we going wrong, or is it the right one? Yeah. Any guess? You can write in the comment. Yes. The three guys are there only, so I'm asking you only. So if you have any guess, you can write or like. Okay. So let me then explain it to you that why it is so that the electron which is at point A will take 49 like roughly 500 days to go from point A to point B, but the light lights up instantaneously. So you can think it like a pipe. There are two ways in which you can think. You can think it like a pipe which is filled with water, fully filled with water. And these are point A and this is point B. As soon as you turn on the supply, what will happen? This molecule which is here, water molecule, will push this molecule, that molecule will push this one, and the B will come out instantaneously. Right? But there will be a time lag which will be there to reach this particular particle from point A to point B. So that's what happened. It's like a tube which is fully filled with electron. As soon as one electron starts moving, the other, which is at the very end, also starts moving, and that is instantaneous. And that's how the current flows, and that's why we see that whenever we turn on the plug, the light lights up instantaneously. That's the very naive explanation. But what actually goes in the system is like you have this tube which is filled with electrons. These are my free electrons, which I'm just putting like this. And as soon as you apply voltage V, remember what you are doing is you are applying an electric field under influence of which the electron moves. And the electric field travels with this, it's an electromagnetic radiation, EM radiation. And electromagnetic radiation moves with the speed of light, that is C 3 into 10 power 8 meter per second. So as soon as you turn on the plug, what happens? The electric field gets generated in the system. And that electric field gets generated in a time of 310 power 8 meter per second. That is very instantaneous. So this electron will start moving. This electron will also feel the force, and that electron will also starts moving. So the conduction comes from the electron which is here, and then that makes a loop, complete loop, and that's why the light lights up instantaneously. Though the electron which is here at this end will take many days to reach from this end to the other end, to A to B. That's the motivation of this question. Otherwise, it's an easy calculation. You all know, you guys can do. But the motivation behind this question is to realize that the electron which is at the one end doesn't move to the other end instantaneously, but the signal propagates with the speed of light. Yeah. If this is clear to you, then I'll move on to the next question. If you have any doubt or question, you can always ask me in the chat box. Now the next question is density of copper is given. Density of copper is 8.94 gram per centimeter cube, and atomic weight is also given. That is 63.5 per mole. That's of course gram. And the effective mass of electron beam, so M effective is 1.0 times mass of electron, free electron. And the question asks me that what is the Fermi energy? That each atom gives one electron. Okay, so they are saying that each atom gives one electron, then calculate the Fermi energy in the system. So the relation between the Fermi energy and the thing we know comes from our class notes also. You can just follow. So they will be h bar square by 2 m star, that is the effective mass, times 3 pi square n to the power 2 by 3. Right? That's how the effective mass, that's how the Fermi energy is related to the carrier density. H bar is a constant. M effective they have given, that is 1.01 times mass of electron, free electron, that will be 1.01 times 9.1 10 power minus 31 kg. 3 pi square is a constant. All I have to extract is the carrier density. So let's extract the carrier density. Density N will be what? Rho, that is the density of the copper, times the Avogadro number by the molecular mass. And that's how we calculate. And we know that density of states will be the Avogadro number, Na we all know from our school books and all those things, that it will be 10 power 23 atoms per mole. It tells you that in a 1 mole of a given system, these many atoms will be there. That's the Avogadro number, right? And M is also given 63.5 into 10 power. If I convert into the kg, it's gram. This is gram, 10 power minus 3 kg per mole. So the N will be nothing but rho is 8.94 into 10 power, it's gram. So gram I will have to convert into kg, or let the gram be gram. So it be gram per mole. And centimeter cube, of course, I will have to convert it to the meter cube. So that will be 8.94 centimeter cube for the 10 power 6. So this will be gram per meter cube. Then Avogadro number is 6.02 divided by 63.5. So if I just do the simple math, let me just calculate. It's 8.94 times 6.02 divided by 63.5. So that will give me 8.4 into 10 power 28 per meter cube number of electrons. That's the N which I will get. If I know the N, second, these are class notes. If I know the N, I'll follow this equation, substituting equation 2 in equation 1. So my EF will be h bar square by 2 m star 3 pi square times 8.4 into 10 power 28 to the power 2 by 3. H bar is 1.05 into 10 power minus 34 joule second. And star will be 1.01 times 9.31, 9.1. So 9.1 times 1.01 is 9.2, 10 power minus 31 kg. So EF will be 1.05 square times 10 power minus 68 by 2 times 9.2 times 10 power minus 31 times 3 into pi square. Okay, let me just calculate this number. Let me just calculate 3 into pi square is 3.14. 3.14 times 8.4, that is 248 to 10 power 28. So we write this 2.48 times 30 2 by 3. My EF is 1.05 times 1.05. Just calculate this. 1.05 times 1.05 divided by 2 divided by 9.2, that will be 0.06 roughly to 10 power minus 31. This is 31, this should be 31. So if I subtract these ones, 68 minus 31, that will be 37, and this will be 10 power 20 and 2.48 to the power 2 by 3. I have to calculate 2.48 to the power 2 by 3. That gives me 1.83. So 1.83 times 0.06 will give me 0.109 into 10 power what, somewhere minus 17. So EF is nothing but 10.9 into 10 power minus 19 joule. And of course I can convert it to the converting it into EV, electron volt. I'll have to divide it by 1.6. So 10.9 I divide by, yeah, 1 second, 10.9 I divide by 1.6, 6.81 EV. And so the correct answer for this one will be 6.81 EV. Roughly say. So this is the one. Any question? Any question like where this relation comes from? This thing I think I have been already been showed in the class, 3 pi square. So this is the mainly relation. Otherwise, you all have to compute this n. N is given as rho times Avogadro number by molecular mass, and then you compute the n. You substitute it in equation 1, that gives you the Fermi energy. Finally, you convert the Fermi energy joule into the electron volt by dividing it by EV, and that gives you 6.8 EV roughly. Okay, if no more question, then I'll move on to solving the next problem, which is the electron density of copper. Okay, so the problem is like 0.47 into 10 power 22 centimeter cube. I want it to the meter, so 8.47 10.28 meter cube per meter cube. And they are saying the plasma frequency omega p. You all know the plasma frequency is derived from, you take the oscillating electric field with frequency omega, and then you substitute it into the Maxwell equations. I'm saying Maxwell. It's a Maxwell standard Maxwell equations, and then you determine the dielectric constant, and the plasma frequency is the frequency which above which, if the frequency is there, the light which you are falling will transmit. It won't decay. It will be oscillating function. But if you shine the light with frequency less than omega p, then due to the screening, all those things, the light will decay into the system only, and it won't be transmitted. And omega p is the frequency, is the plasma frequency above which the transmission happen, and the below which the transmission doesn't happen. And omega p is given as ne square by m epsilon naught. Point to note is that in the class which has been the form which has been derived is based on the CGS unit. So if you convert into the SI units, this is how the omega p will be. And you know the electronic charge, you know the electronic mass me, epsilon naught. You all know that it will be 8.85 into 10 power minus 12, if I'm not wrong, farad per meter, and E is 1.6 into 10 power minus 19, right? This is Coulomb, and M you will know 9.1 into 10 power minus 31 kg, and carrier density is given. So let's just calculate omega p. Omega p will be under root n, that is 8.47 into 10 power 28 times E square 1.6 into 10 power minus 19 square by 9.1 into 10 power minus 31 kg divided by 8.85 to 10 power minus 12. So you calculate the omega p, then first you calculate the omega p, and the frequency, since it's given in hertz, so frequency will be given as by omega p by 2 pi. That's how the frequency is defined. So to find that, it will be 1 by 2 pi times 8.47 into 10 power 28 times 1.6 into 1.6 will be somewhere around, just do it the calculation, 1.6 times 1.6 is 2.56, 10 power minus 19 minus 38 divided by 9.1 into 10 power minus 31 is 8.85 into 10 power minus 12. Let me just solve it. Okay. Yeah, I can do it in the MATLAB also, guys. Leave the MATLAB. I will just do it in the calculator for timing. If the calculation gets big, I'll solve it in the MATLAB, because then it's become more easy for the complex equations to solve it in the MATLAB. But since these are the normal calculation, I'll use the simple calculator. Yeah. So it's 1 by 2 pi times 0.2692 times 28 minus 38 plus 31 plus 12 is 10.33. So 1 by 2 pi times this square root of 2.6 square root of 2.692 is 1.64 times 10 power 16, and you divide it by 2, you divide it by 3.14, so that will gives you 0. to 6 into 10 power 16. Yeah. So that's how it's been calculated, and you can calculate it. It will turn out to be 0.26 10 power 16. This is 1.64 10 power 16 divided by 2 pi. This is the frequency. The question asked was in 10 power 16, the plasma frequency to decimal place you can write it's 0.26, and if it's omega, then you write 1.64. You ask the omega. Yeah. And any question? Any question from your end? Okay, no question, then I will move on to the next problem, which is the final one. The drift velocity of an electron subjected to an electric field of for a relaxation time. I see. So what they are asking is the drift velocity, the velocity with which the electron drift when it's subjected to electric field. They're asking, given is the electric field that is 20 volt per meter, and relaxation time is given to be 10 power minus 14 second. We all know that Vd is nothing but E tau by m. So E we all know is electronic charge, so I will write 1.6 into 10 power minus 19 times 20 times tau is 10 power minus 14 divided by 9.1 times 10 power minus 31. So it's nothing but 1.6 times 20 divided by 9.1. That will be 3.56 into 10 power 19 and 14 plus 14 minus 31 minus 2. Yeah. So you can write it's meter per second, and Vd you can write as 3.56 centimeter per second. That's the drift velocity of the electrons in the given constraints of 20 volt per meter. Any question? If there is any question, you can ask me or write in the chat box. Okay, if there is no question, then I will just quickly go over and we'll cover the summary of today's class. So, yeah. The first question was if the Fermi energy was given, the resistivity at room temperature was also given, and the question asked what the corresponding velocity of the conduction electron and the average time. So conduction electron, we write it at 2 under root 2 E by m, and that gives to be the 1.39 10 power 6. Then the next part was like relaxation time was asked. So tau can be written in terms of the resistivity, mass, carrier density, and the electron like this, and therefore you see this can be extracted. So n we extracted from the EF because we know that EF is given as 3 pi square n to the power 2 by 3. EF we knew in this question, so we extracted the n to be 5.88, and then we extracted the tau. The tau came out to be 3.710 power minus 14. Roughly in the metals, the relaxation time is of the 10 power minus 14 order, and the carrier densities are of the order of 10 power 28. These are the number 10 power 28 per meter cube. So these are the number one should keep in the mind typically because they help in solving the problems. And like some other numbers like 1 MeV corresponds to 10 Kelvin, all those numbers, if you keep in your mind, the calculation gets easy for you. As a condensed matter, like physicist, you or in the material research, you should always remember the temperature and the energy relations. That how much energy corresponds to how much temperature. Like 300 Kelvin corresponds to 25 MeV roughly. Yeah. Then we discuss the band bending, that how the edge state physics is different from the bulk, the whatever that we derive the dispersion relation. They are for the bulk, not for the edge. Edge are there, and the drop is near the contacts. And this is called the hot end, and this is called the cold end, depending like where the current is flowing on those directions. It depends. Hot edge and cold edge is defined in terms of the edge. Then the next question was the average time between the collision and the copper was given. The thermal conductivity at room temperature kappa they wanted to extract. So the K by sigma T we know is a constant, and that is the Weidmann-Franz constant. In question, the constant is given 2.31. They asked what is the kappa. Sigma we know n square tau by m, and we know that what is the tau. N we took the value which is the standard one for the copper from the internet, and then we extracted the K kappa, which is the 380 Weber meter inverse Kelvin minus 2. In the third problem, the density of state function of the electron in metal is given. So GE-DE relation is given, and they ask for the Fermi level at a temperature which is close to absolute zero. So that will be the Fermi energy basically at absolute zero. You calculate, and they have given. We know that n is nothing but the integral of GE-DE. So we integrate this quantity, we get then EF and N relation. We write it in terms of the EF, and we substitute the values of the N, and that gives me the EF to be 4.42. Now in the next question, they ask like, well, consider a free electron gas in a two dimension, the relation between electron density N and the Fermi vector Kf. So for example, our 2D system was like this, Lx and the Ly were the dimensions, and each state will occupy an energy of pi, like 2 pi square by A. For one state, this much area is required in the K space, and total number of states will be, so let me write the G degeneracy, G, G times, the G is the degeneracy, and then we calculate it, and here we show that in a non-degenerate system, the N is related by K square by 4 pi, where is in a system of degeneracy 2, it's K square by 2 pi, but for the systems like graphene, where there is a spin degeneracy also, spin and valley, both are there. So this relation turns out to be n equal to K square by pi, but since in this equation, it's just a simple metal, not like a graphene, and we take the electron spin degeneracy only, the answer to be K square by pi. The next question was, for a free electron gas in a two dimension, the density of state is given by. So we already in this question we extracted the n and k square relation. We substituted the k square in terms of energy, and density of state is nothing but dn by de. So we did this calculation, and that gives me that for spin degeneracy of 2, ge will be m by pi square. In the next question, for a free electron gas in a one dimension, the density of state is given by, so I take it to be one dimension, n is like g times dk by 2 power lx. This is the space you can say is required to fill one K state, and then the energy, then I substitute Kf from this free electron relation, and that gives the N to be the e to the power half and all those things. Then density of state we calculate, and density of state is but nothing but del N by del E, number of states per unit energy, and that is 1 by pi h bar under root m by 2e. In the next question, we discuss the conduction electron density in a copper wire. So so it's a 1 kilometer long wire from end A to end B. Potential difference allowed applied is 6 volt. Electron starts moving from A to B, and the question asks what the time taken by the electron to move from A to B, and the time which we extracted is around 503 days. Then we corroborated it with the observation and all those things, and then we figure out that okay, it's not like that this electron goes from A to B and then only we get the signal. It's like all the electron in the system starts moving, and and the speed at which it happens is the electromagnetic radiation speed, that is the speed of light, and so that's why we get the instantaneous current in the system. And then in the next question, the density of state was given, the atomic weight was also given. We calculated the carrier density using this relation, rho times the Avogadro number by molecular mass. This gives me the like the carrier density in the system. I know the carrier density from the notes from the classroom. We can derive it also. It's not a big deal. We can derive it from the way we did it for the 1D and the 2D. If we do it for the 3D, we take a sphere and then 4 pi k square dk, then we integrate it from 0 to kf. Then we substitute EF is equals to s bar square k square by 2m, and that will give me this relation. You can follow the class notes. For this, we substitute the carrier density n, and that gives me the EF to be 6.81 electron volt. In the question number 9, we looked for the electron density was given, the plasma frequency is under root n square by m epsilon naught. We substitute all the equations, all the numbers of m epsilon naught n. That gives me omega p to be 1.6 into 10 power 16 hertz. And if I convert it to the frequency, like some people call omega p as also frequency. So I think omega p also you can call frequency, but if you go to the units of the hertz, then it's essentially omega p by 2 pi, and this will be hertz. So it's 0.26 into 10 power 16. And I think if it is in hertz, then we'll have to take the omega p only. And omega p will be 1.64 in 10 power 16. Anyway, time inverse is also hertz. So yeah, this you can see. And then the drift velocity is given. The electron is subjected to an electric field. For the relation time is given. They ask what is the drift velocity. Drift velocity we know from the Dode model, E tau by m. Electric field is already given. Tau is given. Electronic charge and effective mass we take it to be of the electron, and we expect Vd to be 3.56 into 10, like centimeter per second. So this is what we did in this class of the TSIT, and with this I will end the class. If you have any question, you can write in the comment box. Yeah. If no more question, then today's class is over. In the next class, I will be solving the assignment number 2, previous year, which you will get some idea, and which will definitely help you in your exams. Yeah. So if there is no more question, you guys can leave the class. With this I will end the class. हाँ भाई, अरे क्लास ले रहे तो बताओ। लेनी पड़ी थी, बताओ। 2 इंच कितनो कितनो 2 इंच मन के बेरो। अरे तो 2 पोर वो तो ठीक से के जो नीचे वो जगह छोड़ रहे अलमारी के, जब 3 इंच से। हाँ देख ले अभी तो भाई, अभी तो बेटी बाप की से देख ले, कहते यही सोच रही हो आगो ठीक से। थोड़ो थोड़ो सा ऊंचो से के हल्को से ऊंचो रह जातो। अच्छा तू कह रहा कि फर्श डलवाना पड़ेगा मतलब। ठीक से रसोई तो ऊंची चंचल हो तो बावली बूथ सी। मैं तो पागल सी। आपा मिस्त्री तो कह रहे कि ऊंची से रसोई। हाँ, तो अभी तो पहले बनाते, बाद में हम तो तुम कर लो। तो बिजी होगो कितने किंगा किंगा कर बजाओगा का काल देख